Hecke is Jan Gier from Gier, and he'll be talking about solvable lattice models, Yang-Baxter, Hecke and Macdonald.
Well, thank you, and thanks to the organizers for inviting me to speak at this memorable occasion. Yes, I met Rodney for the first time in 1999 when I started a postdoc with Murray in Canberra, and I remember that we were traveling via LA at the time, but missed the connection in LA, so we had to stay over. And I think Murray had something planned the day after. And so he arranged for Rodney to pick us up from the airport. And so I was a young postdoc just out of a PhD where I had devoured his book. And so when I arrived in Canberra, I could not believe I was being picked up by Rodney himself. And that sort of continued at the time. I spent 2.5 years in Canberra, and Rodney, and as well as Elizabeth and Murray and many others, have been very generous in giving time to me. So that was a pleasant memory, but Rodney is very down to earth, which was nice. So the last time I saw Rodney was in 23, I think, at the ANZIM meeting in Hobart for the inaugural Rodney Baxter Prize in Mathematical Physics. And so here's a picture of Rodney at this more festive occasion, blowing. And you can sort of, if you look carefully, you'll see famous lines on the cake there. All right. So to my talk then. There are sort of connections between, and several speakers have alluded to this already, between exactly solvable models, representation theory, combinatorics, and many different areas. And I want to describe some of those that relate to my own work. And the first one is related to Macdonald polynomials. And I'm not sure everyone is completely familiar with them, but they are a family of orthogonal symmetric polynomials in n variables indexed by partitions lambda, and they reduce to well-known other families of symmetric functions like Gier functions. I should say they depend on n variables x, but also on 2 parameters, q and t. And when q is t, we get Gier functions. Q is 0, whole Littlewood polynomials, t is 0, q Whittaker polynomials. Then there is a limit to Jack polynomials. And there are also generalizations to other root systems where you can get Korn-Linder polynomials, which are generalizations of Eskew-Wilson polynomials. And most of these polynomials are defined by mathematical properties. They're not necessarily given like an explicit formula, but rather they're eigenfunctions of some commuting system of operators. But what I want to show here, that there's a natural construction of, at least for Macdonald polynomials, using solvable lattice models. For that, we will need the Hecke algebra, and everyone would have seen this in this audience. So the Hecke algebra is a deformation of the symmetric group, where the quadratic relation is replaced by this relation, and there's a parameter q that appears here. And aside from the quadratic relation, there's the braid relation, or I guess many of you will recognize it. Constant Yang-Baxter equation here. These Hecke generators can be Baxterized, so to speak. So you can add a function, a U-dependent function. In fact, use this Q number here. And then this object satisfies the Yang-Baxter equation with spectral parameter. So we're going to need this Hecke algebra in a polynomial form. There's a representation on polynomials, which is this formula down here. So if sigma I is a transposition that just transposes 2 variables, then 1 minus sigma I acting on a polynomial will be divisible by xi minus xi plus 1. So if we divide that out, multiply by this numerator and add q, we'll get another polynomial. And so this defines an action on polynomials, and you have to believe me that that action obeys these relations. So now there are special families of functions that form like a distinguished basis under the action of Hecke. And they are labeled by composition. So composition is just a sequence of numbers, mu1 up to mu(n), where the mu I are taken from some fixed set, 0 to r-1. And a particular basis that I'm interested in, there are many different distinguished bases, but one in particular I call f sub mu, satisfies the following relations. Ti acts diagonally, just as a multiplication with q, if the neighboring indices mu I plus 1 are equal. And Ti acting on f mu produces f of Si mu, where Si is again the transposition of mu I plus 1, if mu I is larger than mu I plus 1. And then there is a quasi-periodic boundary condition, like some cyclic condition that I don't want to give explicitly here. But what I do want to state is that for this family of functions, if you sum over all of these functions, so I'm going to sum over all permutations of a partition. So if I order all the mu's in weakly decreasing order, as per Ole's talk in a partition, and sum over all permutations, all the f's that correspond to this, and the f's have two parameters, theta and q. But q is the q from the Hecke algebra, and theta, I didn't tell you, theta comes from this quasi-periodic boundary condition. You can prove that this is a symmetric function, and it is in fact a Macdonald symmetric function indexed by the partition lambda. So I've used here the notation q because that is sort of Baxter's q, and theta. More common in Macdonald theory are the parameters q and t, and this q in the Macdonald notation is what I have called theta here, and the t in the Macdonald notation is what I call q. So there's an unfortunate tendency that q plays different roles in different communities, and you often have to translate between them. But anyway, there is this correspondence. So I want to now slightly change perspective and form this object here. So I'm going to look at the vector space spanned by n copies of CR plus 1 and take the standard basis in that vector space, and then take the vector that I call capital F here, which is the sum over all basis elements with coefficients, these polynomials f mu, that are solutions of these Hecke relations. And then the Hecke relations, or the action of the Hecke on the f mu, translates into an action on this vector by the R matrix, or rather the matrix R check. So the conditions on the coefficients, little f of mu, are equal to saying if I act with R check on this vector, then that's equal as acting with SI on the vector. And so SI here, this transposition acts on the coefficients of my vector just by swapping coordinates, by swapping variables, xi minus or I plus 1. And R check is a matrix that really acts in the vector space. And this R check, for this example, is the R matrix coming from UQSL R plus 1. So RS1 is the 6 vertex model, but this is a higher rank example. And of course, it satisfies the Danish Yang-Baxter equation. Okay, so okay, all good. Why am I doing this? Well, just to remind you, this is the 6 vertex model, and I'm going to use these pictures to denote the 6 configurations as lattice paths. From this construction, it follows that these polynomials Fu can be identified as cylindrical partition functions of some higher rank bosonic model. I've drawn a picture here. So let me first go to the statement. The polynomial F mu is equal to a trace of a product of what are bosonic row-to-row transfer matrices. And so how does it work in the picture? Each row of my cylinder corresponds to a transfer matrix A indexed by the color that sits here on the left boundary. So I have A green, another A green, but with a different, with X2, A blue with X3, etc. And the configurations on my cylinder are colored lattice parts. And in the vertical direction, so this direction here, there can be infinitely many parts for each color. I can't draw that. I only drew a few as example. And these parts can also wind around. So if you follow the red path here, red path goes over the top of the cylinder, comes around, and then follows here, goes around again, and follows here, and then it sort of ends. So every path needs to end somewhere at a designated endpoint at the top of the cylinder. There's a designated point for each color. That's where they need to end. And every time they go around, they pick up powers of theta, this parameter theta here, or the parameter theta here. So this trace really means tracing over the periodic direction of the cylinder, picking up powers of theta every time you do. So we have a very explicit formula for these polynomials. And from this, if you remember, if I would sum over all these polynomials, I get a symmetric polynomial, which would equal the Macdonald polynomial. So we can do that in the following way. If I take the sum of all row-to-row transfer matrices indexed by every color I, call this script A, then take the product of script A's. It's just a stack of row-to-row transfer matrices, commuting row-to-row transfer matrices, and then take a trace over the cylinder. I get my Macdonald polynomial. So these curly A's commute, and that means this polynomial is symmetric. Yeah, that's sort of the statement. Just looking at the time. Okay, so I want to tell you a little bit more about the explicit construction because it sits at the heart of exactly solvable lattice models. So how do we construct these operators? So we look at the Macdonald polynomial indexed by a partition. We take the largest part, lambda 1. Let's call that R. R stands for rank. And that means we need R plus 1 transfer matrices, 1 for each color, A0 up to AR. So then the Hecke algebra exchange relations that define these polynomials F mu. If I write F mu as this trace of product of transfer matrices, the Hecke relations translate into what are the Zamological Fadeev algebra relations for the vector A, where A is the vector that consists of all the copies of A sub I. So we need to solve this relationship with the right under the right boundary conditions. And that can be done by first looking at the Yang-Baxter algebra. And we need to solve this RLL equation for bosonic L matrices corresponding to a rank R. And if we can do that for each R and form the monodromy matrix as a product of LR, LR minus 1, all the way up to L1, then the claim is that every column of this T will satisfy the Zamological Fadeev algebra. So we go from the Yang-Baxter algebra, reducing the rank at each step to a solution of ZF algebra. So the point being here that, of course, this equation here is very similar to the Yang-Baxter algebra, except that there's no R check on the right-hand side. So just to give you some examples of what this looks like, if in the rank 1 case, we take the 6-vertex R matrix, and I should say we use a stochastic gauge. That was remarked by Tomohiro earlier. Sometimes this is more convenient. The bosonic L operator, familiar to some in the audience, has this form. So phi is a Q oscillator. So I have a phi and phi dagger on the off-diagonal elements, and I take two of them, one with parameter x, one with parameter y. Then the claim is this is a solution of the RLL equation, where in the bottom line, x and y have been interchanged. And we can do this for rank 2. So now we have a 9x9 R matrix, and the corresponding bosonic L matrix looks like this. There are now two families of bosons, phi1 and phi2, with phi2 dagger, and then K is really the number operator corresponding to that algebra. So you can go on like this for every rank. We have a general expression for these solutions. And then what you need to do is take solutions for rank 1, for rank 2, for rank 3, etc. You multiply them, and then you get some vector that now has this boson family in it, that boson family, and that boson. So there are many boson families corresponding to all the colors and all the parts on the cylinder. So I've tried to, give this formula in terms of plaquettes that you're allowed to put on your cylinder, and the colors indicate how the parts can continue through the plaquettes. Okay, so that is the construction of Macdonald polynomials using solvable lattice models, and sort of bringing together these sort of different areas in mathematics and mathematical physics. But they also can be used in applications. And one of the applications that I've worked on quite a bit is this asymmetric simple exclusion process that Tomohiro already mentioned. So this is a process of a classical stochastic process of hopping particles on a circle. So in the rank 1 case, you just have black and white dots, and white corresponds to a hole, or black as a particle, and this would be very closely related to the XYZ spin chains. If you have multiple colors, you're just looking at a higher rank version. And the whole construction that I talked about here can be used to compute the stationary state of the ground state of this Markov chain, namely the probability to see a particular configurations of colors, mu1 up to mu(n), is given by an evaluation of these functions f divided by the Macdonald polynomial, because that's an overall normalization. So the denominator here appears such that if I sum over all configurations mu, this sums up to 1. So I need to take these polynomials and then set theta and all the x's equal to 1 to get my probabilities for the A set. So that's a little application of this instruction. So more recent work that I just want to briefly highlight is the asymmetric simple exclusion process with a boundary. So this was on a ring or a cylinder. So now we go to a boundary. So it looks like this. You have the exclusion process, and I've drawn a left-hand boundary. So the particles here can just hop to the left and right. I only consider black and white in this case. They hop to the black particles hop to the left with the rate 1, to the right with the rate q. But at the boundary, particles can enter, or they can leave the system. So there's lack of particle conservation. So in this case, similar sort of reasoning as before shows that the stationary state is related to quantum interpolynomials. And you can compute the transition probability to go from a particular configuration mu to nu in time t. And also there are results for expectation values that you can compute using the machinery of solvable lattice models. And I think Tomohiro gave a nice sort of history of people who made valuable contributions here. So the fact that you lose particle conservation poses significant technical challenges. They can be overcome by considering this lattice model on the square lattice, but now with boundaries. So we need K-matrix weights here at the boundary. So I'm not going to give you the detail, but of course we're going to choose weights that satisfy the reflection equation, and then try and compute this object with empty state at the bottom and some particle state at the top. And this is possible because at the boundary we allow particles to enter and propagate to the top. So the theorem then is that this transition probability, if your space is semi-infinite, so I should say all this right-hand side stretches out all the way to infinity. So if you have an infinite or semi-infinite system, you don't have Bethe equations. There's no quantization condition. So you can use the freedom in the Bethe equation to integrate over. And this partition function can then be written as a multiple contour integral, where you recognize here the single particle Bethe wave function, just the product over i's 1 to n. So this is the Bethe wave function times a boundary factor. Scattering factors at the boundary, and then some factor that I call G00, and this is the sort of non-trivial pseudo vacuum because we can have ghost particles in this system, and so there's a non-trivial empty to empty probability. So let's go here. If the top state is also empty, so all zeros, I can still have non-trivial contributions because a particle can be created. It can wander through the system and then disappear at this boundary, for example. So there's a non-trivial partition function associated with going from empty to empty, and that is denoted by this. So this is an expression that appears here, which I'll talk a little bit, one more slide, I'll talk about this. From this expression, it's possible, using the work of Johansson and Tracy Witham and people, Tomohiro himself, and people he talked about, to derive Fredholm Pfaffians and find probability distributions that are related to random matrix theory, such as the GOE and the GSE ensembles. Okay, so last comments are on this empty to empty transition probability. It turns out to be the partition function of this triangle. So I put 6 vertex configuration on the both vertices, and then on the boundary I can put arbitrary K matrices. So we have non-diagonal boundary conditions. And so this is a non-trivial object, even though the boundary conditions are 0 on the right-hand side and the bottom. There can still be lattice paths going sort of from one boundary point to the other. So this triangular partition function is like the boundary version of the famous Isogin-Koropin determinant, and you can derive recursion relations for it, and which can be solved using the shuffle algebra. So there's an elegant way of doing that, and it turns out to become this Pfaffian expression. So this sort of generalizes the Isogin-Koropin determinant when you have a boundary. Okay, so I think I should stop here. Just a conclusion. So there's been an extended and ongoing influence of solvable lattice models in, as Tomohiro also indicated, Rodney worked predominantly in equilibrium physics, but in the past 10, 20 years, a lot of results have been obtained in non-equilibrium physics, in particular related to this KPZ fixed point universality class. In probability theory, so it was already mentioned earlier, there's now a new area called integrable probability, where influential people work and derive new results. And maybe Michael will talk about this more tomorrow, as well in combinatorics, as also Ole talked about just now. So I showed you a rainbow cylinder lattice model matrix product formula for Macdonald polynomials, which is very explicit. So unfortunately, we don't have anything like this for corner inner polynomials, which we'd love to have, but there are major technical obstacles there. Applications are to multi-species exclusion processes and transition probabilities for RSET with fully open boundaries. And that's where I'll end. Thank you.
Do we have questions? Any online questions?
Anyone's free to ask there if they want. Yeah, and I just wanted to mention, if you can hear me, right? This is my yeah. So thanks for reminding me of the Baxter birthday cake. Yeah, that's good.
Yeah.
I will show it in the future. Yeah, great. Thanks.
Yeah, well, thanks for organizing that. I guess it was you or Vladimir.
With the help of Yang-Xi.
Oh, Yang-Xi. Yeah. So I hope you can see. Maybe we should zoom in a bit.
Yeah, I have a close-up of it. So
oh, okay.
Just went looking for it.
But yeah. There it is.
Oh, yeah, that's right. You've zoomed in a bit.
Yeah.
So it was a cake with one version of the Yang-Baxter equations on there. The simplest version for someone who decorates cakes, I think.
Right.